Yeah, so today we're going to talk about cluster analysis. We're going to talk about what it is, why it's needed, the key assumptions, and different methodologies, and also apply it on real life data, right? So, cluster analysis is just a multivariate data mining technique whose goal is to group objects based on a set of user selected characteristics. So basically, what we are saying is we might have a sample of data or a population of large data which might be heterogeneous, but we just want to group it into small homogeneous parts. For example, if you look at this chart here, the data is unorganized, but after cluster analysis, it will be organized to come up with maybe a certain number of clusters depending on the constraints that you are looking. So example applications of cluster analysis, it's applied in marketing, land use, insurance, urban planning, and so many applications. So in marketing, it helps marketers discover distinct group in their customer base and then use this knowledge to develop target market. So you might have heard of market segmentation and so forth. So it's just one application. So I'm just going through it so that I don't take much of your time. So those are the notes for the remaining ones. And then we might need to ask why are we doing cluster analysis at the first place. So cluster analysis is just a major tool in a number of applications in a number of market applications in many fields of business, engineering, and etc. It also helps in data reduction, that is to convert large data into meaningful, classified into manageable groups, and also hypothesis generation, hypothesis testing, and also predictions based on a small predictions based on groups. Okay, those are the key assumptions of cluster analysis. But from here, it is important to note that even though they are overall assumptions of cluster analysis, each methodology we use for cluster analysis also has its own key assumptions. Okay, so this slide just gives us an overview of how cluster analysis work. The primary objective of cluster analysis is to define the structure of the data by placing most similar observations into groups to accomplish the task. We must address three basic questions. How do we measure similarity? How do we form clusters? How many groups do we form?
Measuring similarity. Similarity represents the degree of correspondence among objects across all the characteristics used in the analysis. It is a set of rules that serve as criteria for grouping or separating items. So first of all, there's the correlation measure, which is less frequently used, and where large values of others do indicate similarity. Then there's the distance measure, most often used as a distance measure of similarity, with higher values representing greater dissimilarity. Distance between cases not similar. These are not similarity. Then there's the types of distance measure. The distance measures. Number one, there's the Euclidean distance. Number two, squared Euclidean distance. There's the necessity block Manhattan distance. Then the Chebyshev distance. Then the Mahalanobis distance d squared. So moving on, we have the question: how do we form a cluster? So in order to form a cluster, we identify the two most similar closest observations not already in the same cluster and combine them. Then we apply this rule repeatedly to generate the number of cluster solutions, starting with each observation as its own cluster, and then combining two clusters at a time until all observations are in a single cluster. This process is termed as a hierarchical procedure because it moves in a stepwise fashion to form an entire range of cluster solutions. It is also agglomerative method because clusters are formed by combining existing clusters. So, and how do we form a group? There are two examples that we used here. The first one is the nested grouping. As you can see, we have an example of an organization whereby we have the managing director nested around with the customer services assistant, which is Henry, assistant number 1, number 2, Nicola. We also have a development manager with senior developer, assistant is James, junior developer. Then this is just an example of a dendrogram, which is a measure of similarity. So if we start at the base, as you can see on the individual subjects on the x-axis here, we have, for example, A, B, C, D, C, and D, with the y-axis indicating the increasing similarity. So the objects A and B will increase similarity to form a cluster. This will be considered as a single cluster here. It's a small cluster. Then when we go upwards and we join A, B to C, then it's now one cluster, and so on. So there are different methods of clustering. Basically, there are three types of methods that can be used to carry out a cluster analysis. These methods can be classified as follows. Number 1, there's the hierarchical cluster analysis. Number 2, there's the non-hierarchical cluster analysis. Then number 3, there's the two-step cluster analysis. So hierarchical clustering uses the distance matrix as the clustering criteria. This method does not require the number of clusters k as an input, but needs a termination condition. Also, in other words, this stepwise procedure attempts to identify relatively homogeneous groups of cases based on selected characteristics using an algorithm, either agglomerative or divisive, resulting to construct of a hierarchy or a tree-like structure dendrogram depicting the formation of clusters. So as you saw in my previous example, when I was explaining how we are forming a tree like in that dendrogram diagram. So this is one of the most straightforward method. Of course, the hierarchical cluster analysis provides an excellent framework with each to compare to any set of cluster solutions. So there are two basic types of hierarchical cluster analysis. Number 1 is the agglomerative algorithm, then the other one is the divisive algorithm. So the agglomerative algorithm, the hierarchical cluster begins with each object or observations in a separate cluster, right? Then in each subsequent step, the two clusters that are most similar combined to build a new aggregate cluster. This procedure is then repeated until all the points are combined in one cluster. And also the similarity decreases during successive steps. Clusters cannot be split in the agglomerative algorithm. Then the divisive algorithm, we begin with all objects in one single cluster, which is then divided at each step into two additional clusters that contain most two dissimilar objects. the single cluster is divided into two clusters, then one of these clusters is split for a total of 3 clusters. This will continue until observations are in a single member cluster, from one cluster to n subclusters. So this is just a diagram showing on top it's an agglomerative agness type, then there's the divisive, which is can be called the Diana type, then non-hierarchical cluster analysis. In contrast to hierarchical method, non-hierarchical cluster analysis do not involve a tree-like construction process. Instead, they assign objects into a clusters once the number of clusters is specified. So there are 2 steps in non-hierarchical cluster analysis. The first one is to specify cluster seed, identify the starting point, then the assignment, which is to assign each observations to one of the cluster seeds. So then there's the non-hierarchical clustering algorithm, which in short basically sequential threshold method, parameter threshold method, supervised procedures, and all of this concluded into a clustering algorithm known as the k-means. So we also have the 2-step cluster analysis. This is a procedure which is an exploratory tool designed to reveal natural groupings of clusters within a dataset that would otherwise not be apparent. The algorithm employed by this procedure is several desirable features that differentiate it from traditional clustering techniques. There's of course the handling of categorical and continuous variables. There's the automatic selection of number of clusters. Then there's of course scalability in that. Then we also just summing up some real life applications to cluster analysis. We have market segmentation. For example, groups of people can be grouped according to their similarity in several dimensions related to a product under considerations. Then of course there's the sales segmentation. Clustering can also tell you what type of customers and what products. Then we can also find the credit risk, high performers of customers based on their credit history. Then there's the operations, high performer segmentation, and promotions based on a person's performance. Then of course it can be used under the insurance, city planning, and also geographically. So we'll be moving on to the YouTube survey cluster analysis that we used. It's a YouTube survey dataset that we used. So we'll be presenting on how to perform the different types of cluster analysis method.
Okay, so we have imported our data which we want to undertake a cluster analysis on. So basically what this data is, it's just telling us what people look at, what they place importance at for YouTube, for the, sorry, chirungu chatiza, my bundles are here. Alright, sorry, ngatangit. Bundle, English bundle, man. Alright, so yeah. Yes, so this is the data set that we're going to use for cluster analysis. So this data basically tells us about what makes people like a video on YouTube, or what they look for in a video for YouTube. So here, a marketer might be trying to see how he can better market his YouTube video. So basically, we're going to do cluster analysis using 3 methodology. The first methodology is the hierarchical test, and then k-means test, and then 2-factor two-stage test. So to do the hierarchical test, first we go under analyze, and then since it's just classification, we then go to classification and hierarchical cluster. So the importance of doing a hierarchical cluster is that it doesn't take any assumptions to say we are assuming that there are so many clusters. It's a blank sheet, we'll be studying it. So we want to cluster our data based upon these variables which I had selected already. So we just go under statistics, and we see that whether we want any of these tick boxes here, but I'll remove this for now, is we are just doing the hierarchical cluster so that we have an indicative of how many clusters we might need for the two methodologies, right? Okay, so we cancel this, and on plots, we need this dendrogram. So this dendrogram will just give us a visual picture of how the data is related among each other, and so it will be our key focal point here. And also we might need to have the orientation of the dendrogram depending on the space you want. So for now, we'll just go with the vertical outlook. And then we need to choose also the method for the cluster. So there are the number of methods that we can look at, but the method I prefer most is the word method. So the word method, basically, it's more advisable because it tries to have clusters of the same size as compared to other methods. So for now, we just go with the word method. So in our presentation, we'll talk about other different methodologies to look at, but for now, we're selecting this one. And then also the intervals, we just keep the default setting, and we don't want any standardization because since it's a questionnaire, it's already standardized between 1 and 5. So we're selecting none here. And then we, under the save option, we're not saving anything because this is just an input to the two methodology test. Then if you are happy with everything, we just press OK, and here is our output. Okay, so it takes a little bit of time. Okay, so after it is run, the output then tells us that we ran the data entries were 1000, which is 100%, and there was no missing case, meaning that our data was okay in all respects. And then here is the word linkage agglomeration schedule. So this is not as important as it looks. It's just giving us each data entry and the cluster the cluster it falls into. So what we want to focus on is the dendrogram, which is still processing. Let's just give it a few minutes. Okay, here it is. So basically what the dendrogram is telling us is just how the data sets are related. So it's a little bit large, so let me just try to shrink it. So if you want to shrink it so that you can look at everything at once, you just double click, then from here you right click, you just right click the chart. Okay, it's a large data set, so it's taking time. So we say property windows, and then from here we look at the chart size, and then we just remove maintain aspect ratio, and then we sort of change everything from here. This is just try and error until the dimensions fit perfectly. Okay. Okay. Right. So this one is too small, or we might need to change again. Apply. Okay, yeah. Let's see how this looks like first before we proceed. So we then close here and then it starts again. Okay, so we had made our diagram to fit on one page, and from here it's clear that we have a number of clusters here, but now the choice is now based on how many clusters that we want. So to select the number of clusters here, you just place a horizontal line. For example, you can put your horizontal line here at 20, 15, 10, 5, or wherever you want, but that horizontal line will then determine how many clusters we have. So for example, if we put a horizontal line at 5 here, then it means we have these many clusters, like 1, 2, 3. 4, this becomes our clusters. But when selecting the number of clusters that we want, you have to keep in mind the constraints that are included in the objectives of our analysis. So for now, maybe we just try to broaden to say we just need 2 large clusters, because even if you put a line at 15 or 20 or 25 or 10, it's giving us the same number of clusters, which are these 2 large clusters. So we can just go with these 2 large clusters for now. So basically the hierarchical method, it's a top-down approach where it just shows you how everything is linked to each other. From here we just see that we have 2 large clusters which are then subdivided to go down. So that's where the hierarchy comes from. So we're going with 2 clusters from here. We're concluding that we have 2 clusters. But however, to be sure, we also need to undertake the k-means test. So to do a k-means test, you go under classify again, and then here is that k-means cluster. Okay, so I had already selected the same variables which we had selected previously, and then the k-means test is just one weakness, which is you have to predominantly state how many clusters that you want the data to come out with. But from the hierarchical test, we found out that we require only 2 clusters. So I have written 2 here, and then we have to change how many iterations can take. So for iterations by default it's 10, but we want it to do as many iterations as possible, but it will stop as soon as it reaches an optimal result. That's why I put 99 here. Then we say okay, and then under save we just save the cluster membership. So here the cluster membership is will just tell us what cluster the data belongs to. So we can say continue, and we can also move around the options button. So we might need to know what was the initial center, cluster centers before the iteration. So we can tick this here, and also we might need the ANOVA table. So basically the ANOVA table will tell us how significant each variable is in determining the cluster, and then we can remove this cluster information for each case, because we'll find it on the next test that we'll do. So we say continue, and then press OK. So like we said, the k-means test is based on iterations where they just place random to say cluster starts here. So basically what we are seeing here is the mean. At first they just say the mean must be here and the mean must be here. So it then does iterations to see which is the correct center for each cluster. Each variable, they just put these 5s and then 1. I mean, you could have chosen 4, 3, but you would all come up with the same result. So that's what we're getting here. And also this table here just tells us the number of clusters, the number of iterations done to come up with an optimal result. So the optimal result is when the change in cluster center is now at its minimum, which is at its absolute minimum, which is 0. So from here it just shows us that 8 iterations were done, and on the 8th iteration, that's where we had the most minimum change in the cluster center. And after the iterations is then tells us what are the cluster centers for each variable, which is 4, 4, 4, 4, and so forth. So if you want to get a visual impression of this, you can just double click and then come up with whatever funny chart that you want. But for now, let me just choose this. So we see that these are two perfect clusters. And also we can look at the ANOVA table. So for the sake of time, I'm just rushing through all the output, as I assume that we might have covered this in other modules. So the ANOVA table is just saying that this variable is statistically significant by looking at an alpha of 5% or 10%, but just as a core, we can go with 5%. So it tells us that this variable has been significant in determining the cluster. Because this one is less than 5%, but however, this one wasn't as significant. It wasn't significant at all if you're considering alpha of 5%, but an alpha of 10%, it then becomes significant. But as the benchmark is 5%, this hasn't been significant, the second variable, and the rest of the variables were significant in determining the cluster. And last but not least, we have this table that just tells us the number of entries in each cluster. So cluster 1, it is just 354 items, and cluster 2 is 656 items. You see that the second cluster is bigger than the first one, and every item, which is 1,000, out of the initial 1,000 has been taken into account. There is no missing data entry here. So basically, this K-means test is also supporting that this data can be clustered into only 2. That 2 is the perfect cluster. So to just look at the data entries again, we have selected save. So it is basically saved where each cluster belongs. So let me just go to the far right. So it's telling us that this data entry 1, it belongs to cluster 1, and then cluster 2, cluster 2, and so forth. So maybe to just wrap up, I'll just look at the last methodology we have to look at today, which is the two-step cluster. So to do this one, you just go under classify and then two-step cluster, and then you select the variables. So these variables are continuous variables, not categorical. That's why I've put them here. And then the distance measure, you can put whatever measure you want, but we've gone with the log likelihood so that it acts as a standardization parameter. And clustering criteria, we've gone with the base criteria, but this one would have done for now, but I just prefer this one. And then under options, I haven't selected anything, and then the output. So this is basically a model. So that's why I'm just keeping the default settings. Battery. And then after I press OK, so this just so this is now our output. So this output, the advantage of using this two-step cluster is that it doesn't come up with an assumption like the K-means test, where we have to determine the number of clusters, but however, it does an iteration so that it tells us how many clusters we have to look at. So for me, it's telling us that the 2 clusters are the optimal results, and also the quality of our data or our model generally is fair, which is good enough for live data. But if it was poor, we might start questioning our model. So to see the more detail on this model output, we can just double click the model. Okay, so under the cluster model, it supports the information that we got from the K-means test to say that the sample size for cluster 1 is 64%, and the sample size for cluster 2 is around 36%. So that's just the model summary. So we can actually go further in detail and try to look this, what variable is the number of clusters. So from here we see that this variable, the input matrix, we see that this variable has the most impact in determining the cluster, and then this one is the second most impact. So I mean, to get a better visual appreciation, it just shaded in different colors, right? So we can also move around here. Okay, it's quite a big model, that's why it's taking time. Okay, so we can also move around here to see maybe cell distribution. Okay, so this is telling us the response we actually get versus the average response per that question, and so forth. So actually I was also looking for cluster comparisons here. Let me select the number of clusters. So this is actually supporting the fact we are seeing here to say that this variable is the most significant in determining the cluster, in determining the number of clusters, because here we are looking at the median, which is to the far left, and the median for the second cluster is to the far right, meaning that these numbers are too distinct. And this also applies to here, but it's not the case for the variables which we say they are less significant in determining the cluster, which is this one, what video is about, because the medians, they are sort of almost the same. They're actually the same if we just move around here. So there's a lot of important information that we can maybe consider. Is also the predictor important. It just shows us what the factor, the importance of the factor in maybe predicting which clusters to come up with. So it's sort of supporting this information. So we see that this one is here, and then it has the most predictive power. We can just select here to say we want those with the most predictive power, and so forth. So I think that's it from me. Thank you.